So today we're going to look at bond energy. So we're going to ask ourselves this question. When fuel is burned, energy is released. Where does that energy comes from? So take a time to think about this. Where is this energy coming from when we burn a fuel? So in order to answer this question, we're going to have to look at bond breaking and bond making. So to get an idea of this, let's imagine we have our wine glass. Well, it's not my best drawing, and this is the wine glass intact, and this is a broken wine glass. For this wine glass to be broken, this wine glass had to absorb energy. So some energy source must have come in, shoot in, bang, shatter our glass, and we end up with a broken wine glass. So whenever we have bond breaking, we know that energy is absorbed. The same thing is true for the opposite. If we have bond formation, energy is given out, the opposite. So to break a bond, we need to absorb energy. And try to remember this thinking about this wine glass. This wine glass is not gonna shatter by itself. It must have absorbed some energy for it to be broken. Okay, so the same concept with a bond. So if we have a bond is actually two atoms sharing an electron, and to break that bond, you need to have the, the molecule must have absorbed energy. Okay, so let's say we have a methane, CH4, and it's reacting with oxygen to form carbon dioxide and water. Let's first check if this equation is balanced. We have one carbon here, we have one carbon here, we have four hydrogens here, we have two, we're going to need a two here. Remember, when you're balancing the equation, you can only put numbers in front, the coefficients. Okay, so now we have one carbon, four hydrogens, four hydrogens. But let's check our oxygens. We have two oxygen plus two oxygen. We have four oxygen on the product side, and we have two here, so we need to multiply two here. So now this equation is balanced. So remember, these are our reactant, what we start out with, and the product is what we end up with. So we're going to look at a diagram to illustrate how this really looks. So here is our methane, one carbon followed by four hydrogens. One carbon with our four hydrogen bonds here. So on this diagram, our red dots, red circle represents our hydrogen. On our shaded um, dark spot represent the carbon. So we have two oxygen. So oxygen bonds, oxygen bonded to another oxygen is a double bond. So that's why we have two lines, because this is a double bond. So we have two, so we do two diagrams. And we have carbon dioxide. Here again, we have a double bond between an oxygen, a double bond between another oxygen. This is our carbon dioxide. And we have two water, one oxygen to two hydrogens. And we have two water molecules. Okay, so this is our diagram illustrating what is taking place. You should be able to draw a diagram like this. You may have to reference, if you don't know how the diagram looks, you may have to reference Lewis diagram to have an idea. But you need to be able to do this to answer some of these questions. So bond breaking requires energy, and so it's an endothermic reaction because we're absorbing energy. And bond making release energy, and that's exothermic. Okay. So here's a table showing the average bond energy per mole of bonds. And when we say an average, because we have to take an average, because the bond to break one CH bond, the first one, is going to be different from the bond to break the third one. But if we take an average, we have an idea how much it is to break a CH bond. So here we have just some basic things. We have a hydrogen to hydrogen bond, single bond. The bond energy is 432. Carbon to hydrogen 413. So you can just look at this diagram to get an idea of the bond energy for each. So you may look and see any patterns or see anything that you notice to break different bonds. So let's look at a equation here. So we look at the formation of water. So hydrogen and oxygen combine to form water. So if we're drawing our diagram, so we have a better understanding how it is, a hydrogen H to a hydrogen H1H is a single bond. It's two of these hydrogen bonds. So we have two diagrams here. Oxygen, again, oxygen is a double bond. We have only one because there's only one oxygen molecule we have here. We have two water molecules, and the water molecule is made up of an oxygen to two hydrogens. So we have two. So in order to do this, to find the net energy exchange. So if we want to see how much energy is involved for this process, this is the process we're going to use. We're going to use what is the calculation called the net energy exchange. The net energy exchange is equal to the summation of the reactant bond energy minus the summation of the product bond energy. So we're looking at reactant, then we're going to look at product. So let's look at the reactant bond energy. For the reactant, again, these are the reactant. We have two hydrogen to hydrogen, and we have one oxygen to oxygen. So we're going to look for the hydrogen to hydrogen bond energy and see what it is, what value is associated there. If we scroll up, we say hydrogen to hydrogen is 432. So since it's two of these bonds present, we're going to multiply 432 kilojoules by 2. And we also have an oxygen to oxygen double bond. We're going to see what's the bond energy for that. And if you look at that, that is 495. It would have been incorrect if we use this. This is for a single bond. 495 is for the carbon oxygen to oxygen double bond. Since we have only one, we're going to do a summation. We will get a total of 1,359 kilojoules. Now we're going to look at the summation of the product bond energy. So looking at the product side, what do we have? We have hydrogen to oxygen, hydrogen to oxygen, hydrogen to oxygen, hydrogen to oxygen. So we have four of the same kind of bond. All right. So we're going to write 4 oxygen to hydrogen bond. So we're going to look back at our diagram to see what value, or table, to see what value is associated with the oxygen to hydrogen. We realize it's 467. So it's going to be 4 times 467. We're going to do our calculation. We plug these numbers into our calculators, and we're going to get a total of 1,868 kilojoules. So if we go back to our original equation, the net energy exchange is equal to summation of the reactant energy minus the summation of the product energy. So that's 1,359 kilojoules minus 1,868 kilojoules. Again, we plug these values in our calculator, and we realize that we have a total of minus 509 kilojoules. So this reaction, the formation of water, when we have hydrogen and oxygen to produce water, we have a total, a summation of 509 kilojoules. The negative sign means energy is given off. It's an exothermic product. Okay. So we could look at a diagram to see what this looks like. These diagrams are called energy exchange diagrams. We use these diagrams to track energy exchange during a chemical reaction. Okay, so we're going to first look at exchange for exothermic reaction. We always start with our reactant start at 0. So we draw a line for a reactant start at 0, and we're breaking bonds. Remember, we always have to break bonds first. We break the bonds, and based on what value you put your value here. Let's say the example we just did. So the reactant product, we should have 1,359 kilojoules. So we could have put this 1,000 here, 1,359. So that's the amount of energy we took to break the bond. To form the bond, let's see what we had. To form the bond as the product side, 1,868. That's 1,868. That is for the formation of the product. So to find the net energy exchange, since this is greater than this, our product line is going to be further below the reactant line. So if you take to find the net energy, you subtract these values, and you're going to get the same 509, and it's negative because we are below the 0. So this is minus 509 kilojoules. So that's how you do an exchange for exchange diagram for exothermic reaction. This is a typical one for exchange for endothermic reaction. Again, this is a reactant. We start at 0. This is the energy absorbed to break the bond. We absorb energy, and to form the bond, we release energy. If it's an endothermic reaction, we're going to release less energy than we started out with. So this will be our net energy change, which will be in a positive value. Of course, this will be our product side. All right, so that's how you do your diagrams. Hope this helps, and you can draw an energy diagram, and you can also do your calculations to calculate the net energy exchange. Good luck.